Okay, we're back with our final video. I'm going to do the extra practice problem 7, 8, 9, and then let you see a copy of the answer sheet for the worksheet real quick. The worksheet has a few challenges that you won't have to face on the test. So there'll be some good to know stuff and then some need to know stuff. So we're going to look at these three molecules. So this we've got, on your sheet it says CCl2S. So how did I figure out which one to put in the center? Well, carbon has 4 electrons, so 4 empty seats. Sulfur has 6 electrons, 2 empty seats. Chlorine each have just 1 empty seat, 7 electrons in their valence. So I put the one with the most empty seats in the middle, that's carbon. The chlorines, of course, fit around easily because their one unbonded electron just fills right in. Then I put the sulfur over here, and you can see that it's obvious that the carbon and the sulfur share this one. The only thing that's not quite as obvious right here, these two that are still unpaired, so they'll join together and form a double bond between the carbon and the sulfur. So when you draw the line structure, you'll get carbon with a single bond to chlorine, and then because of this pair being shared and this pair being shared, you have a double bond between the sulfur and the carbon. So that's CCl2S, like that. Put that carbon in the middle because it has the most empty seats. So then down here, if you look, we've got silicon with 2 sulfurs, so that would be called silicon disulfide. You have to use the prefixes since it's a covalent. Silicon has 4 in its valence, just like carbon, and then sulfur has 6 in its valence. So I placed them around. You can see they fit in nicely here, but silicon is going to bond its unshared electron with this one from this sulfur, and its other unshared with this one from the other sulfur. So that gives us some nice symmetry. So we've got a single bond here, and then a double bond here, and a double bond here. So it'll turn out to be S double bonded to Si, double bonded to S, and then you've got your 2 unshared pairs hanging out there. So silicon feels like it's got 8 in its valence, sulfur 1, 2, 3, 4, 5, 6, 7, 8 in each of its. Symmetry is important. We've got symmetry here, so that kind of confirms that we're on the right track. So that's silicon disulfide, 2 double bonds, 1 for each of the sulfurs. Number 9, carbon bonding to sulfur. Carbon's got 4 in its valence, and sulfur has 6 in its valence. So you can see, where's my red pen? You can see these 2 will bond, right? And then these 2 will bond, but then you still have this and this unshared pair in the carbon. So they're actually going to come together and form another bond. So you're going to get a triple bond. This one's really tricky. It just takes experience with things like this to figure out how that happens. So carbon's actually going to get a triple bond there. And then, that only gives it, that's not what's going to happen, is it? Is that what's going to happen? That's very strange. I don't like that. I'm not feeling good about this. So these guys aren't going to do that. I guess it's going to be one of these guys. So carbon will keep its unshared pair. That gives us symmetry, and we would have violated the octet rule if we had brought this pair over, because then sulfur would have had its 2 unshared pairs plus a triple bond. That would have been 2, 4, 6, 8, 10, and you can't have 10. So this way, we keep all of our electrons. We get 2, 4, 6, 8 for the carbon and 2, 4, 6, 8 for the sulfur. And that's the best structure we're going to get there. since we have such a strange number of electrons, because we had, 4 from the carbon and 6 from the sulfur, so 10, how do you share 10 things around 2 things? Well, 2, 4, 6, 8, 10. 10 things shared around 2 things. That's the only way to do it. So yeah, that's just a really strange one. Some of these just take some thinking. Remember symmetry, remember putting the one with the most seats in the middle, and remember the octet rule. You cannot do something like this, like what I was about to do. Right? Because carbon would have 2, 4, 6, 8, 10 electrons around it, and carbon would only have 2, 4, 6. And that violates the octet rule for both of those. They would never do that. So that would be completely wrong. So this would be the Lewis structure for, well, what's its name? Carbon monosulfide. So that would be a triple bond. Then the last of the extra practice problems says, look at these. What would be the hardest one to break based on the Lewis structure? Well, anything with a triple bond is going to have the highest energy bond. That will be the hardest to break. So I would say this carbon monosulfide would be the hardest bond to break because it's a triple bond. And none of the others had a triple bond, although this has 2 double bonds, which would, cause it to have a lot of energy there too. So basic rundown. Now I will grab this and let you have a look at it. So here's the worksheet I emailed you. And if you look, PBr3, so phosphorus tribromide. Can't get focus. Let's see if I can hit the button and make it focus a little better. No? Okay. So phosphorus tribromide is a pretty easy Lewis structure to draw. Phosphorus will start out with 5 electrons around it. The bromines will just each fill in 1. You'll get a bunch of single bonds. Focus. Please focus.